Hey guys, I just wanted to go over a little bit about Bronsted Lowery acids and bases, being that that is the main definition that we'll be using. Um, Bronsted Lowry acid donates one hydrogen, and that's really the main thing you got to keep your head around is that it's always only going to be one hydrogen. Every acid and base reaction that we work on in AP chemistry is just tracing the movement of one hydrogen. Now, there are certain acids that give up more than one hydrogen, but you get it in two steps. So it gives up a first one, and then you get another step that moves up the second one. So just if you think about it like that, it really simplifies a lot of the processes, especially when we start studying acids and bases more in depth and we start getting some formulas. If you just remember, all you have to do is keep your head straight on the fact that one hydrogen is being transferred. Now, some acids, we call those strong acids, they readily transfer their hydrogen. Those they do it up to 100%, but those are very few. Um, Hydrochloric, hydrobromic, hydroiodic, and then with your oxy acids, acids with oxygen, anything where the oxygen is two more than the hydrogen. So a good example is nitric acid, HNO3. You have three oxygen, one hydrogen, and so 3 minus 1 is 2. That's a strong acid. H2SO4, sulfuric acid, or if you've probably seen that one before. 4 minus 2 is 2, so the reason why they call those oxy acids is because you have oxygen with your hydrogen. And why those protonate so readily is that oxygen pulls, because it's very electronegative, and it pulls field away and allows that hydrogen just to pop right off of there. But like I said, there are very few strong acids. Strong bases, also very few. You've got your alkali metals when they form a hydroxide, so like NaOH. That's really the one that you see most often. And then some of your group 2, your alkaline earth metal hydroxides, will also be considered strong bases because they do ionize 100%, but they're not very soluble in water, and so that's kind of an issue. So let's see, we've talked about transfer of one hydrogen, strong acids and bases versus weak acids and bases. A weak acid, a weak base, most of it just stays together. Like hydrofluoric, because it's got that hydrogen bonding, kind of stays together. And so, whereas this 100% goes to nitrate, NO3 negative 1, and H plus, and here you eventually, over 2 protonations, the first one goes down to HSO4 negative, and then you get that second hydrogen kicked off, and it's SO4 negative 2 with another H. All of it, all the hydrogen, it all just divides. But here, most of it just stays HF, and there are, a few H's and a few F minuses, but not enough to be anywhere near 100. And so we talk about that as a weak acid, even though it still is very corrosive. You'll get more into that when we study acids in the second semester. But right now, what you need to be aware of is how to identify Bronsted-Lowry acids and bases, and also how to write a reaction with them. So here, and I'm going to actually change something here. I'm going to add the AQ, L for liquid, AQ, AQ. That's going to be important later. We're not going to use it this unit really, but just get this idea that the NH3 is here and it's dissolved in water, and then you got water, which is a pure liquid, and then you've got this, which is dissolved in the water, and this is dissolved in the water. So this is kind of the solvent. That's how you got to look at that. Now, so when you look here, NH3, he is, and you can just draw an arrow like this. Boom. Okay, so this becomes this. And you can see that here he has 3 hydrogen, and then here 4, so he's gained a hydrogen. So this, because you gain a hydrogen, you're going to be a base. Okay? And then since the base changes and gains a hydrogen, that becomes the conjugate acid, which makes water the acid and the OH the conjugate base. And so if you look at that, yeah, we would consider that the conjugate base, because if you remember the OH, that's a basic part, okay? That's like the NaOH, the OH, the hydroxide ion is the basic part. So there you go. Now, there's one other thing we need to talk about, and that's the idea of something being amphoteric. And so if something's amphoteric can be an acid or a base. Amphoteric can be an acid or a base. And so water here is an acid, and water is really the amphoteric substance that we talk about most often. There are other ones. HSO4 can either gain a hydrogen or lose a hydrogen. But water is really the perfect amphoteric substance because it will go either way. HSO4, that's part of sulfuric acid, so it wants to get rid of that other hydrogen. But water, it's neutral. It'll do whatever you put it with. So if we put HCOOH plus H2O, AQ, liquid, and then COOH negative, it's going to be an AQ plus. Okay. So when you look here water acted like an acid because it donated a hydrogen. But here, this hydrogen right here is, you can see it starts here, but then it's over here with the water in the second step. So this is your acid. And then you look at that, he's missing that hydrogen, which makes him a base. Okay? So that's my acid. That's my conjugate base. And then water here, even though he was a base, or even though he was an acid the last time, I almost got myself, he's going to be a base this time and form the conjugate acid. So you see here, water is an acid because he gives the hydrogen. Water gives away a hydrogen here to this ammonium ion. But here, water accepts the hydrogen from the formic acid. Incidentally, that's the kind of acid that ants have. If you get an ant bite and it stings right there. So there's 2 good examples of a Bronsted-Lowery acid-base reaction, and as a bonus, amphoteric, something that can be an acid or a base.